Hey, welcome. Today, we're going to crack a fundamental code in chemistry. I'm talking about a single number that can tell you the future. Well, the future of a chemical reaction, anyway. We're going to get to know the equilibrium constant K.
So let me ask you something. When you think about a chemical reaction, do you kind of picture it as a one-way street? Reactants on one side, they do their thing, turn into products, and boom, that's it, story's over. Well, the truth is, for a ton of reactions, it's way more interesting than that. It's more like a two-way conversation.
And that's where this idea of chemical equilibrium comes in. You see, a lot of reactions are actually reversible. The products can literally turn right back into the reactants they came from. And eventually, they hit this amazing sweet spot, a point of dynamic balance. The forward reaction is happening at the exact same speed as the reverse reaction. So, to our eyes, it looks like nothing is happening. But underneath the surface, it's a constant dance.
Now, this idea has been around for a while. You have to go all the way back to 1864. Two Norwegian chemists, Goldberg and Waj, were the first ones to figure out how to describe this balance using math. And what they came up with is now, seriously, a fundamental concept in all of chemistry.
So how did they do it? Well, they gave us what we now call the equilibrium law. And a great way to think about it is as the official codebook for a reaction. It's the key that lets us translate what's happening inside a flask into one simple, really powerful number.
At its core, the law is just a simple comparison. It's a way to mathematically relate the concentration of the stuff you make, the products, to the stuff you started with, the reactants, once everything has settled into that state of equilibrium.
Okay, so here's what it looks like in general terms. Now, don't let all the letters throw you off. The big A, B, C, and D are just placeholders for different chemicals. The little letters out front are just the balancing numbers you'd see in the equation. But the most important part, that double arrow in the middle. That's the universal sign that tells you, hey, this is a two-way street.
And this is the secret. It's beautifully simple, right? The equilibrium constant, our magic number K, is just a ratio. It's the concentration of the products divided by the concentration of the reactants. That's it. That fraction tells us so much.
All right, let's look at the full-on expression. Remember those little balancing numbers from the equation? Well, they have a special job here. They become the exponents. So you take the concentration of each chemical and you raise it to the power of its coefficient from that balanced equation. Products on top, reactants on the bottom.
So theory is one thing, but let's see how this plays out in the real world. There's a classic experiment using hydrogen iodide gas that just perfectly shows how incredibly consistent this K value really is.
So check this out. Scientists took sealed flasks, kept them at a constant temperature, and ran 3 totally different trials. Trial 1, they started with only the reactants. Trial 2, they went the other way and started with only the product. And for trial 3, they just threw in a random mix of everything. And what happened? In every single case, the reaction reached a balance point that had a mix of all 3 chemicals.
All right, so here's the big question. They measured the final amounts of everything in each of those flasks, and then they plugged those numbers into our equilibrium law equation. So what do you think they found? Did they get a different K value every time? They got 49.8 every single time. This is the aha moment. It's incredible. It didn't matter one bit what they started with. Once that reaction hit its natural balance point for that temperature, the ratio of products to reactants was always the same. It is a true constant, and that really drives home the most important takeaway here. It does not matter if you start with a mountain of reactants, a flask full of products, or just some random mix. At a given temperature, a reaction will always march towards the exact same equilibrium state, its own unique K value. Okay, so now that we've got the main idea down, there are just a couple of quick rules of the road we need to remember when we're actually writing out these K expressions for ourselves.
Rule number 1 is my favorite because it's so easy. When you're writing the expression for K, you just ignore pure solids and pure liquids. You just leave them out. Why? Well, because their concentration, think of it like their density. It doesn't really change during a reaction. So they're treated as a constant, and we only include gases and things dissolved in water in our final calculation.
Now, rule number 2 is the big one. This is crucial. While K doesn't care about what you start with, it cares a lot about temperature. If you change the temperature, you change the value of K. A perfect example is making ammonia. At room temperature, K is huge, over 400 million. But if you crank up the heat, it plummets to a tiny, tiny fraction. Temperature literally changes the destination of the reaction.
All right, so we know how to find K. But what does the number itself actually mean? This is the fun part. Let's decode the value of K and see what it tells us about how a reaction is going to turn out.
The size of K tells you the whole story. If K is a really big number, way bigger than 1, it means the reaction heavily favors making products. At equilibrium, you'll have mostly products. If K is a tiny number, a small fraction, it means the reaction favors the reactants. It barely even gets going. And if K is somewhere around 1, well, you're going to have a nice balanced mixture of everything.
And when I say huge or tiny, I really mean it. The K value for burning carbon monoxide is a number with 91 zeros after it. That reaction basically goes 100% to products. On the flip side, if you try to break down water at 1,000 degrees, the K value is a decimal point followed by 9 zeros and then a 7. At equilibrium, almost nothing has happened. It's still pretty much all water.
So, that's the bottom line. The magnitude of K gives you a direct snapshot of the reaction's final destination. The size of that number tells you right away whether you should expect a flask full of product or if the reactants are pretty much going to stay as they are.
Which brings me to a final thought for you. Imagine you're an environmental chemist. You're trying to design a reaction that takes a nasty pollutant and turns it into something harmless. What kind of K value are you looking for? Do you want a really big one or a really small one? The answer to that question really shows you the practical power of this one simple number. Thanks for joining me.